you very much. Thank you for the kind welcome, and thank you, Renee, for hosting me and Anna and others back here in Wurzburg and meeting a lot of friends. I guess this is a fairly general audience, so I will try to keep things very simple, but okay. But please feel free to, if you have an urgent question, ask during my talk or towards the end. All right. So this is about the influence of quantum entanglement in many body systems, and my own interests have been in solid-state physics and superconductivity, but it turned out quite remarkably that thinking about quantum entanglement in that context has had, especially in recent years, quite a connection to advances in understanding quantum entanglement in black holes. And I'll try to give you a summary of, biased summary of where we are on some of those questions today. Okay, but let me begin by just recalling some basic principles of statistical mechanics or solid-state physics, which we use every day as solid-state physicists, really going back the basic ideas to Boltzmann. So one of the basic, of the two results of Boltzmann that I want to just recall, one is the statistical interpretation of entropy, that entropy is related to the logarithm of the number of states available to any system. And so in the quantum system, then we can talk very precisely of the density of states, the Hall states, and that's then the exponential of an entropy. So this becomes, of course, this is something Boltzmann reduced by studying classical gases. Classical gases. But it became of great attention in string theory and quantum theory of gravity when Hawking introduced the Hawking entropy of black hole. And so then immediately the question was, what is the statistical interpretation of this Hawking entropy? And that's been a question on which now there's a much better understanding. And in fact, Boltzmann survives, quantum mechanics survives as far as anybody can come. Okay, the other important foundational work by Boltzmann a few years later was his theory of the dilute classical gas and how, apart from when the molecules in this room interact with each other, that leads to various dissipative properties like viscosity, like the increase of entropy. And he wrote down an equation called the Boltzmann equation, which describes this seemingly irreversible phenomena. So this is expressed in terms of some distribution function, f of p, the number of particles at position r, momentum p. And the left-hand side is just a way of rewriting Newton's equations. And the right-hand side was Boltzmann innovation called the collision term, where he assumes that the particles collide with some cross-section just p squared. And the central assumption in his equation was that you could take the probability distribution of the incoming particles, momentum p and p1, to be just the product of their individual probabilities. So this means that we don't need to know whether these particles collided earlier or not. It doesn't matter. All memory of the previous collision has been lost. And so the test of collision is statistically independent. So this is sometimes called a molecular chaos assumption, and is really the crucial ingredient in the Boltzmann equation. This other term here is just the opposite process. So there's perfect time reversal symmetry. That's what was remarkable about Boltzmann's work. Everything was time reversal invariant. There was a Hamiltonian evolution. Energy was conserved, and nevertheless, you got increase of entropy. Okay. All right. So this is all well-established principles that I'm sure you've seen in your solid-state physics course. The remarkable thing is that Boltzmann's calculation for a dilute classical gas also apply after the invention of quantum mechanics to a dense gas of electrons. And it's essentially the same equation. As you can see, the left-hand side looks the same. And the only difference is if you look at the collision probability here, This depends on the probability that these two states are occupied. So quantum mechanically for electrons, all you have to do is put the 1 minus f's here, which guarantees that these states are empty. So you just have to put in the exclusion principle. And beyond that, there's no fundamental change to the structure of Boltzmann's equation. So basically, in a dilute classical gas, collisions are rare, and molecular chaos can be assumed because the gas is dilute. In solid state physics, the gas is not dilute at all. It's quantum, it's very dense, but the Pauli exclusion principle then makes the collision very rare, because any given state at a given momentum is almost always occupied or empty, except near the boundary, the Fermi surface, and that's what allows you to, the Boltzmann equation to still apply. So anyway, it's not an understatement to say that this basic equation, with modification, of course, by Landau and also by BCS in the theory of superconductivity, but beyond these relatively minor modifications, this equation is the foundation of everything really in solid state physics, I would say up to the 1980s. And so somehow we can, even in most solid state materials, you can ignore the interference between successive collisions. All right, so and so, for example, one of its successes has been the fact that the resistivity of most metals and this, and you can then ask, when, okay, suppose the collisions become more and more frequent, when will Boltzmann's picture break down at low temperatures? And there's some kind of self-consistency argument that you can see that this collision time, the time between collisions, tau, should be bigger than this time that you can make out of Planck's constant and the absolute temperatures. Now people call it the Planckian time. And as long as this tau is much bigger than h bar over kt, we now we expect Boltzmann or some modified Boltzmann picture should work. Okay, so that's the foundation of solid state physics. But now we turn to, of course, in the 80s, one of the amazing discoveries was cuprate high temperature superconductivity. So these are materials where the electrons primarily move on a square lattice of copper ions. So that's very simple, even though the crystal structures can be quite complicated. And then they go superconducting at a certain density of electrons in that square lattice, where P is determined by, in this case, the oxygen concentration outside this square lattice. Then at the right hole doping, you can get critical temperatures as high as 100 Kelvin, and that's, of course, so this happened, discovered during my postdoc years at Bell Labs, and I'm still working on them. So this opened up a whole host of problems, one of which, of course, is why is TC so high? I don't think we have an answer to that yet. Instead, we've been addressing simpler questions, some of which I'll say something about today. So now if you go above TC, then you get, at large doping, you get a stage we call an ordinary metal, where the Boltzmann-Landau theory seems to apply quite well. But if you go above the critical TC, the highest TC, which is where you want to study, then you get what's called a strange metal, and this is the focus of my discussion today. What is this strange metal? And the reason we are obsessed by it is because it is this strange metal that gives you, as you lower temperature, high temperature superconductivity. We do have a very good theory of how superconductivity develops at low temperatures out of ordinary metals. That's the BCS theory. But that's not, it's clear that even from this picture, that's not going to be the driving force going to be the main thing we need to understand. All right, so what's so strange about this strange metal? Well, many things are strange, one of which, of course, most famously is the fact that resistance, rather than going as T squared, as it does in copper, it goes linearly in T. And there are many other properties which I won't discuss here, except briefly towards the end maybe. But let me just mention one recent experiment a couple of years ago by the group of Brad Ramshaw. So here they measured, so I won't go into the details, they measured how the the resistance varies as a function of angle in a certain high temperature superconductor in the Straits metal regime. And from this angle-dependent magnetoresistance, they could read off what is the time between collisions. And here I just focus on the isotropic component of this. This is the angle in which the electrons are flowing in the plane. The isotropic component they found was very close to the Planckian bound. So tau was almost h bar over kt within 20%. So even the coefficient alpha was just was close to 1. So to remember that in an ordinary metal like copper, if you do this measurement, the left-hand side would be much smaller than kt. That's the condition for the validity and applicability of the Boltzmann approach. So we're somehow well out of that condition and seem to be entering some more universal behavior where the time is controlled by just temperature, and any fundamental energy scale associated with the coupling constants of the energies of the interaction between the electrons don't seem to appear. Okay, so that's one of the mysteries that we would like to address, among others of the straight map. All right, so since it's clear that we can't use a Boltzmann-Landau description, where we are neglecting collisions between interference between successive collisions, we need to really account for quantum interference between collisions, or it's called today entanglement among the electrons. So there I want to introduce the SYK model, a version of which I introduced in 1993, very much motivated by the puzzles I presented to you. I mean, they were already becoming clear, these issues were important then, although now the data is much better and the puzzles have, so it's, anyway. So what is the SYK model? Well, at that point, my thinking was, well, let's not try to solve the two rates, it's too hard. I just want any simple model that goes beyond Boltzmann, that allows you to account for many particle entanglement in some dissipative regime in some self-consistent way. You know, is there some simple model that you can solve where you can do this? So we want the analog of, you know, of Boltzmann's equation. Boltzmann was solving the simple problem of dilute classical gas, and so is there some opposite limit where you can where the current is carried not by individual electrons but by this entangled many-body state? Okay, so that I just described the model in the new improved version proposed by Alexei Kitev. This is what it looks like. Imagine you have electrons on some random positions. These could be orbitals or anything, and you occupy some fraction of them. So the purple dots are the electrons. I'm ignoring the spins here. And now these move around. They quantum tunnel from one position to the other. Now, normally, an electron would just be free to hop. But once you put that in, we know how to do that. You end up with eventually a theory which at low temperatures, the Boltzmann-Landau theory applies. So the only thing we're going to impose is that no electron can move on its own. So the tunneling processes, if they happen in pairs or more of electrons. So for example, you know, electron from site 11 and 12 could tunnel to sites 5 and 14. And so there's an amplitude for that process, or call it a collision, and this can happen. Or any other process can happen, and each one of these has a different amplitude for it to happen. And now we don't want to neglect the quantum interference between all of these. We don't want to think of these as rare events. This is all that happens. It happens all the time. And we want to understand the many-body state that you're going to get. So this is a very difficult problem. If you want to put it on a computer, you would need, you know, there are 10 n sites. You would need an order 2 to the n by 2 to the n matrix that you have to diagonalize. You know, even the best computers today, above 40, you can't do that. Or even 20 or 30 actually, this kind of problem. So that's a very, very difficult problem to determine the spectrum and understand what happens in such a system with lots of complicated interactions. So the essence of the SYK model is to simplify things a little bit, but it turns out simplification is not that unusual actually if you're thinking about a real system. We're just going to take these numbers and assume they are statistically independent random numbers. That's all. So that each one of these numbers has some value, and I'm just going to assume that every one of these numbers, there's n to the 4 of these numbers, that they're statistically independent. Drawn from this, let's take for simplicity the same distribution, but independently. There's no correlations between them. So that's an assumption made to solve the problem. It turns out, amazingly, that many things can be worked out once you assume they're statistically independent. Now, it may well be that there could be some correlations, and the real world is always correlations. It may well be a system where they're not independent, and that the same behavior still applies. Probably it does, in fact. Unless you take some very special set of numbers, the random case will probably describe what's happening. We don't have a proof of that, and there's no way to prove it because there's no one can solve the problem when you have some set of correlations between these numbers. But other than full exact diagonalization. But let's just take to be statistically independent. So here's a more formal statement of the problem. If you know the second quantization approach, really, this is a complete statement of the entire problem to a mathematician. There's some fermion operators and anti-commute, and this is the Hamiltonian spectrum you need to know. There's a chemical potential if you want, and then there's these numbers. Let's take them to be average 0 and mean square value u. Okay, so anyway, once you pose the problem this way and ask for the larger limit, it can be solved. And now we know a lot about not just the larger limit, we know about corrections and even exponentially small corrections in there. And understanding those corrections, in fact, requires theories of quantum gravity. And I will perhaps introduce a little bit in a few minutes. Another important thing about this problem is that it's strongly self-averaging. And I don't really need to do an average. I can just take one sample with n to the 4th u alpha beta gamma. Most of its correlation functions will do the same. I don't need to take more than one sample. And that's already clear from a lot of numerical work. And the reason it's so strongly self-averaging is because there are so many states in Hilbert space. Not about an n, but e to the n, which is a ridiculously large number. So it just averages very, very quickly. All right, so how does it proceed? Well, you can, in fact, the simplest way to do it is to write down the Feynman expansion. And you find when you average the graphs that only one term survives in Dyson equation. So the entire equations are right here. If you don't know Green's functions, no worries. So there's some sort of integral differential equation for the spectral density of the electrons. And so it looks like, well, we wrote down this equation in 93. I said, no problem, we can solve this in a few days. Well, we're still learning new things about these equations. In fact, hiding in these equations is some knowledge of Einstein's gravity and quantum gravity. That's only something that's been understood in detail in the last few years. All right, so but as written down, these equations to leading order can be solved, which we already did in the early days. And among one thing you find, which was extremely, for us at least very motivating, if you compute the electron spectral density, this is in the half-filling case, you find that the line width, as you can see from the scale, is just kT over h bar. So you very naturally get in this very simple model, generic Planckian times for line widths and dissipated phenomena. You can, of course, now this has been looked at in many other properties, but this is the simplest thing. And the point is that this line width is independent of the strength of the interaction. So that's direct contrast to Boltzmann, with the Boltzmann collision term depending on the square of the collision cross section. So all dissipated times, the time tau, dependent on the rate, dependent on the square of the interaction. Here it's not, doesn't matter what U is. As long as KT is smaller than U, this is what. All right, so now we want to go beyond the density of states. I'm actually going to talk about black holes first, because that's where the connection is quite close. Okay, this is my most technical slide. Here we want to go beyond this large N limit and really understand the full theory, not just 1 over N corrections, but even non-perturbative corrections. And the way that's done is by writing down some finite path integral for this object here, which is a bilinear of the fermion creation and annihilation operator summed over all sites. So you can write down some action for it. And what comes out at very low energies, this frequency in this Planckian regime, you find that this action has a certain symmetry, which is broken by certain terms in a very interesting way. But this symmetry here, we can call as a time reparameterization symmetry. That is, you could have the ordinary time, which is tau, and then you could have clocks run differently. You could have another time, sigma. So sigma and tau turn out to be completely, it doesn't matter which one you pick, at least initially. At very low energies, you find that you could work in the tau frame or the sigma frame, and the equations for G or G tilde look exactly the same. And this is very reminiscent of what happens in gravity and general relativity. You can have space-time reparameterization invariance, and Einstein's equation looks the same in any frame.
Can I ask a question?
Yes.
So you somehow jumped, you had the correlated entanglement quantum pairs, but
Yes.
now you have green function, which is single particle like.
Well, I've noticed there's no expectation value. This is a bilocal field. It's just.
I see.
It's a
So there is
fluctuating
no
field.
expectation. Okay, I see. So you're saying is that it has the non-local information inside.
Yes, it does. Yeah. So it's just a reformulation. This is an exact statement of the problem. No approximation have been made yet. At least this form of it. I haven't told you what S effective is, but if you know what it is, I can write it down later. So this is a theory which so far is essentially exact. And it's just a simplification. So here what we are assuming self-averaging, which can be checked numerically, it does work. So, and what we are assuming is that they're self-averaging, and then these numbers are independent random numbers. And that allows you to reformulate it exactly in this much simpler looking theory, where you just have one bilocal field. Whereas initially you had n electrons, so you had to write down a path integral, all n of them. You don't have to, assuming self-averaging. That's the beauty of it. Okay, so there's this time reparameterization symmetry, and this just gives you a hint as to why there might even be a connection to quantum gravity. But still thinking about this, suppose I now try to compute, anticipating the connection to black holes, the many body density of states. So you just take the system and you diagonalize. So here's an example. This has been done. These are all the states. I think n was 16 or something, so 2 to the 16 states. And you look at their distribution as a function of energy. So you get this curve, and then you can zoom into the ground state, and you get still pretty dense states. Okay. So you can ask, what happens when your energy is extensive? So that's the regime, of course, that Boltzmann is always studying. You have an infinite system where energy and entropy are extensive in the system size. Here it's proportional to n. So there you do find, as Boltzmann said, that the density of states is the exponential of the entropy, which is extensive. And there were calculations that we did where we computed this entropy as a function of temperature. It's a linear function of temperature. And what was surprising then was that there's a constant here. S0 is non-zero as temperature goes to 0. So initially you might say, well, no, this is a problem. In fact, we were very worried. This is a problem. It violates the third law of thermodynamics. But it doesn't really, because of you're thinking about the order of limits. It doesn't mean that the ground state is hugely degenerate. As you can see here, the ground state is not degenerate at all. Instead, what's happening here is that there are many, many low energy excitations, which are exponentially dense. Yeah. The states are non-degenerate. And this is very generic in the problem. In this problem, anything can collide anywhere. You find exponentially dense levels. And this already gives you a hint that the whole quasi-particle idea of Landau, that you can just think of a dense electron gas as a dilute gas of excitation near the Fermi surface, it simply cannot work here because there's just not enough quasi-particle states to give you so many low energy excitations. So what's happening instead is that there's some complicated many body states from here to there, and one state is no relationship to the other. They're just a huge Hilbert space of dimension 2 to the n, and it's some other wave function in this huge space. We don't really understand in any deep way what's going on, but we can compute various things about it. So among the things, yes.
On each finite system, you will get zero. You will get zero.
Yeah, so that's a good point. So it's a question of order of limits. If you take the n goes to infinity limit first, and then say to t to 0, then you will get S naught. If you take the opposite limit, which is that take a finite system, take temperature to 0, entropy will be 0. So there's nothing, yes.
But for topologically degenerate ground states, you always will also notice that the level spacing exponentially decreases. So if you have a topological ground state manifold from the topological ordered state, then if you make the argument here, to take the limits that you just proposed, that would probably be misguiding us for the topological entanglement entropy, right? Because there we indeed want the degeneracy.
Okay, that's not a ground state. You're talking about a system with n quasi-particles. Then you have the ground state is 4-fold degenerate, period.
Yeah.
End of story.
It's not an extensive degeneracy, but the level spacing is exponential in system size.
Yeah.
In that sense, it's similar.
There's no n in front.
No. Well, the level spacing, but there's only 4 states.
Yeah.
Here, in fact, we know I have a complete formula. There's an exponential. If you take an energy window of order 1 over n, there's still exponentially many states. In the topological system, it's still 4 or 5 or something. Yeah, I mean, there's another way to think about it. Suppose I take a non-abelian state and I put in m quasi-particles. Then there are there are exponentially many states at low energy. Exponential number of quasi-particles, not in the ground state. And for a while, I was thinking there was some connection, but I don't think there is. This really has to do with chaos, and it's very different physics from non-abelian quasi-particles. Anyway, so we know if the detailed form of the density of states, and this whole formula, it actually comes from quantum gravity. And various people have contributed. This is a group of Steve Schenker that found the Sinch square root of energy form. So when E and N are extensive, then this argument is very large, and you go over to this formula right here, you get this formula right there. But now this holds even when you're sub-extensive, down to spacing perhaps of order E to the minus N. And there's a free factor and all of this. Okay. All right, so now what I want to do is now switch gears, where we're going to ask the same question about black holes. So in black holes, Hawking and many subsequent works got this answer. But until a few years ago, it wasn't known, in fact, until last year, what is the generalization of this answer for black holes? And for certain class of black holes, now we know. Okay, because we have a detailed theory of the quantum equation. All right, so let me go to black holes. So of course, I just to remind you what a black hole is, it's a solution of Einstein general relativity of some mass m, but it's a solution in free space. And as long as you press the mass m smaller than the horizon radius, then light would be trapped inside the horizon. Everything would be trapped. And so this is a very, very dense object, because for the Earth's mass, the radius would be 9 millimeters. So you have to compress the Earth to the size of a pea to make it a black hole. But there are many such black holes out there, as you know. In fact, it's even worse than that. If you take Einstein's theory and suppose the star is collapsed into a black hole, it doesn't stop. Once the matter has gone past the horizon, it goes all the way to the center. So Einstein theory predicts an infinite singularity with matter of infinite density at the center of a black hole, which is why people were extremely skeptical when black hole solutions were found that this had anything to do with the real world, but today we know it does. I already said that, but in any case, it was clear that when you have this matter of infinite density, Einstein's equation must break down. Classical mechanics has to break down. We have to do a quantum theory. We don't have any understanding of the interior of a black hole. It's not something that can be answered in classical mechanics because it's ultimately infinitely dense matter, and infinitely dense matter or infinitely strongly interacting matter. Now we have an example of such a thing. Infinitely strongly interacting matter, it forms a very strange kind of many-body state. Okay, so then the first application of quantum mechanics was Hawking in 1975, 76, where in modern terms you would say he considered the following problem. Well, it would take an EPR pair of electrons and imagine that one half of the pair falls into the black hole and the other half is outside. Now, since there's nothing special happening at the horizon, we expect the quantum entanglement between these two electrons to still survive, one inside and one outside. So if I'm an observer outside the black hole, I can never ever know what's the state of that particular qubit inside the black hole is. Rephrase that Hawking's argument. And so to me, this is a random qubit. And so I have a random qubit in my hand every time there's a EPR pair forming across a black hole horizon, and the randomness Boltzmann told us gives us temperature and energy. So, okay, this is the baby version of Hawking's argument. In fact, Hawking did much more. He gave an exact formula for the entropy associated with this entanglement across the horizon. And the beauty of his calculation was he didn't have to know what's really inside. He could just work outside the black hole and look at these entangled pairs on the horizon, and from that deduce what the temperature had to be and what the entropy had to be. So one of the remarkable surprises, although Bekenstein had anticipated this, was that the entropy of a black hole is proportional to its surface area. And from this simple picture, you can understand why, because it's the entangled pairs across the horizon, and the density of this is proportional to the area. But it's very, very different from any quantum system that, say, Boltzmann may have studied or Landau may have studied, where the entropy is in the volume. So something very different about a black hole entropy. Okay. So more precisely, here's the temperature, here's the entropy. And there's another thing you can deduce once you have the Hawking temperature. You can look at, well, suppose I throw a star inside a black hole, it's going to oscillate a little bit and then become a perfect sphere. How long does it take to do that? Or when two black holes merge, they have something called the ring down time. Well, this is known, and if you compute this in terms of Hawking temperature, you find it's Planck. Okay, so there's, at least to me, that was one of the first hints that all this non-quasi-particle physics of the SYK and other models was somehow connected to black holes, because this time, Planckian time, seemed to appear again, which we've now seen on theory of strange matters. Okay, all right. So now let me say a bit more about. In fact, the connection can be made much more precise. And let me say a bit more about how this proceeds. So we're going to consider generic black holes in Einstein gravity. We're going to ask that they have a net charge Q. So this rules out probably any black hole out there, but it's an allowed solution of Einstein's and Maxwell's equation. They have a net charge. So the charge, of course, left to its own would explode. The charge is repelled, but mass attracts. So as long as the charge is not too large, the object can be stable. Okay. And the reasons for this will become clear. I won't go into the details, but charged black hole has a certain simplifying feature that I will need. So, if I didn't know anything, I would say, yeah, this is all you got to do. Yeah, you have a space-time metric, G mu, you have electromagnetic field A mu, write down the Einstein-Maxwell action, this is the classical action. And then Feynman told us you stick a 1 over h bar in front of it, and then you integrate over all possible metrics and gauge fields. And this is what you got to evaluate with the boundary conditions of a black hole. All right, nobody knows how to do that even today. But nevertheless, Gibbons and Hawking said, we don't care. We'll just take the saddle point. We'll just take this Einstein-Maxwell action. We'll solve it at the saddle point and then evaluate the action. And that will give us the partition function in some approximation. So we don't know what the question marks are. And this will be the Bekenstein-Hawking entropy, the exponential of the partition function. Okay, and that's a very quick summary of what Gibbons and Hawking did in 1977. One important point about the calculation is it's done in imaginary time. So if you take a black hole metric and do imaginary time, then it has this, it looks like a cigar as shown here. First of all, imaginary time becomes finite and a circle of circumference h bar over temperature against Planckian time again. And the space-time just closes off, like a cigar ends at the horizon. So you only have to do the path integral outside the black hole. So this, and why that should work and really capture the degrees of freedom inside the black hole, well, that's what we're trying to understand. But this is what they did. So once you formulate it this way, the calculation is not that difficult. And you do it, and for a charged black hole, you fix the charge Q and you take the temperature to 0. You get this expression here, which I showed you earlier. But here, in this case, the area depends on the temperature. So if you now expand that out, you get a constant plus a term linear in temperature. All right, so this, of course, was known since 1977. Well, actually, for charged black hole, it was worked out by Schnabel et al. But the calculation was already there. The Gibbons and Hawking paper, its assets. And now I want to, okay, so this is the answer. So now the question is, okay, you've got an entropy by this computation outside the black hole. How does this, what degrees of freedom are we talking about? Doesn't seem to be anything obvious. We're just doing integral over empty space outside the black hole with some boundary conditions, but whatever degrees of freedom there are has to be the dense matter inside. What are these dense degrees of freedom and why do they have this universal answer? So the short answer is we don't know what the degrees of freedom, probably the string theory. But nevertheless, certain features of the answers don't depend on exactly what's inside. That's what's a strong hint from Bekenstein-Hawking calculation. And in fact, many features of the answers don't depend on the detail. That's what the understanding is. Many things, in fact, are independent of the details. And that's why some simple model like SYK can also capture it. So let me try to lead you through that connection now. Okay, so this is what I just said. You got the entropy having a constant, this term linear in temperature for a charged black hole. For a neutral black hole is different. And then you can't do the next. So this result, I learned about it in the early 2000s. And then I noticed at that time, it reminded me of something I had worked on earlier. I mean, the SYK model didn't even have a K and nobody knew about it, except me, I think. So I was the only person at that time, luckily, in 2010, who both remembered the SY model and knew a little bit about black holes. So in this paper, I said, well, certain mean field gapless spin liquids. Okay, that's exactly what's now called the SYK model. Our states of matter realizing these near horizon physics of right and Nordstrom meaning charged. All right, so what's going on? So if you solve the Einstein equations for a charged black hole, this is called a Reisner Nordstrom black hole, you find a very special feature, which is as you go close to the horizon, this zeta is the radial direction and omega is the angular direction. it turns out these directions decouple. All the low energy physics is essentially in the zero angular momentum mode. You don't have to worry about exciting the high energy mode, you just have to worry about a single radial direction. So there's a factorization of space-time. And so you really need a theory along one space and one time directions to understand the low energy physics or low temperature physics of a charged black hole. So that's life. So that's really the key reason for focusing on charged black holes, because they're simpler. The problem for the generic neutral black hole is still open. Okay, so this is kind of another picture of it. This is the same zeta direction. Out at infinity, you have four-dimensional space-time, but very close to the horizon, space-time factorizes into this two-dimensional space-time called ADS2, and a transverse direction, which is this geometry of a sphere, or S2. So going back to the path integral that Gibbons and Hawking approximated by the saddle point. This is the path integral of a three space and one time dimension. It turns out you can exactly map at low energies this to a theory of gravity in one space and one time dimension. So this is a purely classical calculation, which could have been done by Hawking and Gibbons. I imagine if they thought of it, you could obtain some effective action for a theory of gravity in one space and one time, which today we call the JT gravity theory for Jacques and Pagelsbaum. Jacques passed away like last week or something. So anyway, yeah, I don't quite remember the reason they were studying it. Anyway, so you get a theory of gravity in one space and one time dimension. So life in one space and one time dimension is simple, because I told you, what do you mean by area in one space and one time? Well, the area of a black hole is just a point. So to understand the entropy of a black hole in one space and one time dimension, I just need to understand entropy at a single point. And what is the SYK model? But effectively a many-body state at a single point, because there's no sense of space, everything is interacting with the other thing. And it turns out it's more than that. If you take this G path integral that I talked about earlier, that is in fact, it can be rewritten. If you take this 1+1 dimensional theory, now in 1+1 dimension also there's no graviton, so you can actually very quickly fix the gauge and make the theory on the boundary only. You get a theory on that one point, and the theory turns out to be exactly the theory, with no corrections, that you got as a theory of time parameterizations of the SYK model. Let's not worry about that. So this is the time parameterization f of tau. In this case, it's somehow representing the quantum fluctuation of this boundary. So the quantum fluctuation of this boundary in time are in fact described by the same theory that describes the lower order states of the SYK model. It's exactly the same theory.
Sorry, can I ask a question?
Yes.
Regarding 1+1. So if I'm not mistaken, because this is not a specialty, we transfer from 3+1 to 1+1.
Yes, you can only do that in low energies, yes.
Yeah, but when you speak about black relations and everything, so from solid state physics, there is a very different physics than in 3.
Yeah, sure. I mean, so it's a very special physics of this ADS2 metric. So the saddle point characterizes, and all of the low energy excitations are in the zero angular momentum mode. Once you take finite angular momentum around the sphere, you have to pay a certain energy cost. So those finite angular momentum modes will contribute to this ... But it turns out that do not correct the linearity term or the constant.
So just one dimensionality doesn't really affect much. Okay.
Up to order T, it does not. So these two terms here don't care about, if you want the T, there's higher order terms here, this T squared, T cubed, then you have to worry about those things. But up to these first two terms, it doesn't matter. So the statement is, if you start with this theory in 1+1 dimensions and just do classical gravity completely honestly, or you start from this theory, you'll get the same answer.
Okay, fine. If it is completely
There are no corrections to the first two terms. Yeah. But it's more than that. You can even go, so that was all at h bar equals 0 because you did these saddle points. All of those were the h bar equals 0. You can now actually do this full pattern. This full pattern is done. because from tricks we learned from the SYK model, it's the same kind of thing. So in fact, this is the answer now. The final form obtained only last year by Luca Eliasiu, Samir Murthy, and Joaquin Toriachi. And you notice there again, there are three terms. There's an exponential, this is the oldest term, the Frankenstein-Hawking term, it's exponential of the area. This is the analog of the S naught. And the density of states is exponentially dense down to zero energy. This is the sinh term is exactly the same. So the sinh term is related to the gamut, this linear T term. From this coefficient, you can read off what the sinh has to be. That's because the theory is the same as the SYK theory. And finally, there's a prefactor. And this prefactor of area, that's the only thing that depends upon the matter content of the universe. So the fact that the universe, as far as we know, is made up of the standard model and things at much higher energy. The standard model only comes into this number 347 only. No, nothing else matters. Now, of course, there'll be many other corrections. Higher terms which are down by powers of energy and down by powers of the area. For all of that, we have no idea. We may need string theory to go beyond this, but all these terms are basically no. No. All right. And okay, so let me also mention the competition. There was a beautiful calculation in string theory of charged black holes of the entropy. And this was done in black holes that have supersymmetry. They have extra symmetry, which is not present at low energies in our world. It may be present at high energies if string theory is right, but that's irrelevant. They assume it was present down to low energies. So in that calculation, you can compute the density of states, and you get a very different answer. You get an answer when you do violate the third law of thermodynamics. You get a hugely degenerate set of states. There's an exponentially large number of states with exactly the same energy. So in the topological state, the coefficient will be 4. Now here it's exponentially large. And this happens because of supersymmetry. We understand that very well. And even if you take a supersymmetric SYK model again, you would get the same features. So all of this, and all of these corrections to string theory only gave the exponential. All of these corrections here are very well understood. Only in the last 2 years, by there's some beautiful papers by these young people that are mentioned. Okay, so that's really all I have to say about black holes. Oh, just a few more pictures, I suppose. So the idea again is that since our space-time and space is only one-dimensional, all my entanglements right here. And so it seems that to capture that entanglement, you take the simplest possible model of many-body entanglement at one point, and that's the SYK model. And so maybe there's an SYK model in the center of a black hole. No, not really, but anyway, it's not a bad starting point to assume there is. All right. Okay, so how am I doing on time? 10 minutes? 10 minutes, yeah. Okay. So now I want to come back to what started my, so this is a nice detour for me. There have been many other uses of black holes in condensed matter, as you can learn from Joanna and Renee. But so far I've described how the SYK model has actually, the knowledge has flown the other way, but from condensed matter we have learned new things about black holes. Now I want to, but the original problem is still there. What is this strange metal, and how do we describe its physics? Okay, so in 10 minutes, well, I just give you a flavor. We can't literally apply, it's not as simple now. I can't just literally take the SYK model and deduce some of the properties and learn something about black holes, because unlike black holes, your worry is much more germane. I cannot reduce it to a zero-dimensional problem. You really have to solve a problem in 2 spatial dimensions. Certain black holes turned out zero dimension was fine, zero space. Okay. All right, so we have to know a little bit more about what's going on. So in this case, in this pink region, we believe there's still a lot of arguments, but we believe in this pink region is yet a third type of metal, which you think of as a spin liquid. And so let me just explain what a spin liquid is. And in our picture, what you now have to do is do a theory of the transition from this spin liquid state to the ordinary Boltzmann-Landau metal. And that transition is what's responsible for the strength map. Okay, that broad statement I don't think is controversial. The particular theory that we propose uses SYK-like methods to actually make a few predictions here, or post-predictions. So let's start here. At half filling, you have where P is 0, and you just look at the square lattice of copper ions, then what we know from experiments and theory, that these electrons form what's called an antiferromagnet. The blue circles are the copper atoms on which you can place one electron. All the other electrons are not important because they're all paired up, but this unpaired electron can point either up or down, and they point up and down just like the squares on a chessboard. So that's what an antiferromagnet is. But this is an approximation. In reality, of course, electrons want to form singlets. If you just had 2 electrons, their ground state would not be just up-down, they would be entangled into this spin singlet configuration. But the trouble is when you have a square lattice, there's many ways of forming spin singlets, even among nearest neighbors. So here's one way, and here's another, and here's another, and here's another. And so these are all, no electron has moved. The electron just entangled slightly different. So this is another type of many-body state, quite different from the SYK state, but it's another state with long-range entanglement, which we call a spin liquid. And it's sort of, the baby example is benzene, where you just have 2 configurations of double bonds on the hexagon. Here it's an entire square lattice with an exponentially large number of things that are entangled. And in some very precise sense, as we understand extremely well today, there's long-range entanglement in this state. So the spatial structure is, of course, the key. So now we want to add in a few charge carriers. We want to remove a few electrons so that charge actually is moving. So this state, even though lots of things seem to be moving around, nothing is moving. Charge is not moving. It's only motion in some abstract quantum space. It's a state with some sort of spin correlations, but nothing is moving. Here, well, except maybe energy is fluctuating. So here I put in removed a few electrons. This is what happens when you change the oxygen concentration. And now you can, in addition to the resonating valence bonds, you can have the motion of charges. So there's a charge that's moving, but now notice that the charge is moving, but no spin is moving. That's just a charge E. So this is very unlike what's called a hole in a semiconductor, because when a hole moves in a semiconductor, it carries both charge and spin. Here, a hole is moving, but no spin is moving. So this is what we call a holon. So one proposal for the pseudo-gap state, which was made early on, that it's these holons could form a metallic state with a Fermi surface, and maybe that's what's responsible for the pseudo-gap. The only trouble is, we know for sure that that's completely incompatible with other photo emission experiments, because we can tell from various experiments that what's moving in the pseudo-gap is actually charge E and spin a half. So how do you form such a state here? Well, you can create excitations, which are these spin a half particles we call spin-ons, and these can also move around, but it costs a certain energy to create them in a spin liquid. But what could happen is that the spin-ons and the holons would attract each other and gain a lot of energy by forming a bound state. So each one of these green dimers now is a bound state of a holon and a spin-on. It's this wave function, which is another word for an electron. So I seem to have done a lot of work. I split an electron, the holon, spin-on, and I put it back together. Well, not really, because not every electron did this. Only density P electrons have been reconstituted. So this is the state we call FL star, where now these dimers are moving around, but there's also a spin ring. Okay, so this sets up a possibility of a phase transition from this doped spin liquid that I just described for you, which we call FL star, and an ordinary metal. And so to summarize, as a function of doping, we postulate that there's some underlying quantum phase transition, where you go from the state of these green dimers, which form a Fermi surface of size P because of the dilute density of them, and a background of blue spin liquid. Or you just form an ordinary Boltzmann-Landau Fermi surface, which must obey something called the Lagrange theory. All right, so we have developed some theory of how this transition might proceed. It's another complicated theory, and one important actor in it is a certain boson, phi, and the fluctuations of the bosons are very important, and it's like a Higgs boson. And this Higgs boson, when it condenses, then you get the FL star state, and when it's not condensed, you get the FLs. All right, so we have to do a theory of transport, therefore, of electrons coupled with this boson. And this is where, again, the SYK model comes in, because we also want to put in some randomness. These are all, none of the crystals are perfect. Going very fast, I realize that, but there's something called the Yukawa SYK model, which is very much like the toy model of interacting bosons and fermions. I just gave you a model of interacting fermions. There's another model which has interacting bosons and fermions, but there's no dispersion of either the bosons or the fermions. But there's a coupling, the Yukawa coupling G, which is a random function of the boson and fermion wave. This can, in fact, be solved completely, very much like the SYK model, and almost the same problems. So that's the preamble to our recent paper, where we took electrons coupled in two spatial dimensions now, coupled to this boson, this Higgs boson phi. Again, a problem that many people had studied, but our innovation here was to take this coupling and allow for spatial fluctuations between them. Okay, so this there's a G squared, which gives you the fluctuations in G from point to point. There's many reasons from experiments for suspecting that such a thing could happen. So you just take this model and you turn the crank the way you've learned from the SYK model, and lo and behold, you get almost everything that's observed, although we're not quantitative yet. You get a linear T resistivity. There's many other properties for the experts, the specific heat, the optical conductivity, the photo emission, marginal Fermi liquid behavior. All of these come out from this very simple theory. Well, after the facts. All right, so that was a 10-minute summary of many years of work. But I'm excited that we're finally perhaps achieving the hope of the original proposal of understanding entanglement and strongly interacting with many body systems in two spatial dimensions and understand something of experiments. So, yeah, so really the topic of this talk has been multi-particle entanglement. In the SYK model, gives the absence of quasi-particles. In the spin liquid, you get rather different physics, fractionalization and new emerging particles, and perhaps high temperature superconductivity. That's, of course, the main open problem. And all of this has led to new insight on quantum theory of the interior of black hole. I'll just leave it at that. Thank you.
Yeah, it's beautiful. Really nice talk. Questions.
So what do I learn about quantumness, the quantum black holes in these dimensions? Because all the equation of quantumness, all the equations you showed, it was similar to the.
Well, I mean, so I think I would say that up to this point, we're just evaluating the saddle point, which is all that was done by Frankenstein and Hawking and Gibbons and many other people. It was semi-classical. It was semi-classical. A semi-classical theory of the outside of a black hole, where you got an entropy, but you didn't know what the density of states was, how it depended on energy, for example. But at this point, now you do the full pattern. You give the 1 over h bar of that. So you're really doing full quantum mechanics of this coordinate theory. And it's that full pattern interval that gives you this cinch. And so this cinch squared of energy is new. Well, I think it was first obtained by Steve Shanker's group, new meaning now almost 8 years ago, soon after Kitayev's work. And this, notice that it's an h bar squared. It's even more quantum than okay, depends how you measure energy and so on. But it is, it's much more quantum than the Frankenstein-Hawking answer because it now gives you the envelope of these states. Now, so what you're getting is the density of states is a function of energy. We didn't know what that was before. If you had asked I'm sure this is true, you asked a string theorist, what is the density of states as a function of energy for a black hole, charged black hole? They would have said, oh, they all have the same energy. It's a delta function. That is not true. It's not true because of these quantum effects, many-body chaos, and I give you the Now, you can ask an even finer question, but what about what's every energy level? Sorry, you can't answer that. Even for the SYK model, to know every energy level, I have to know all the couplings. Now, I'm not saying that your random couplings inside a black hole are probably surely not, so you really would have to know string theory to get every energy level. But that's too hard a problem. No, but you can. It's almost impossible to do that. But if you ask for the correlations between the levels, they have random matrix statistics, they have this envelope, all of these things can be worked out. And so those are all very quantum effects and now are known very precisely in this enemy for charged black hole. The corresponding questions for neutral black holes are much more complicated because what happens in neutral black holes is that low energies, in fact, they're not black holes. There's something called the Hawking-Page transition, and the energy level spacing is much larger. It's only above a certain temperature, a certain energy, that you get dense levels with black hole extents. So that's much harder to study because you can't just start at low energies. You need something at intermediate.
So in this model where you have now you cover SYK, which is
Yes.
more or less you exchange boson between electrons and you get superconductivity. And I'm guessing this transition, which
Yeah.
you were showing some optical predictions and some RPS predictions. Are they consistent with the experiments? Or?
Yes, yeah. So this is above TC. They're not gone.
Yeah, it's above. It's just the strange metal description.
Yeah, in this whole regime. In fact, this whole log behavior here in the optical conductivity, this came out after our paper, and this was Michaud and all analyzing optical data very carefully as a function of frequency temperature, and they found forms exactly. I mean, okay, I wouldn't say it's a prediction, but that paper didn't exist when we wrote our paper, and they just somehow this is how things happen. Things happen at the same time. The fact that this is a marginal Fermi liquid has been known for a while, and that also comes out. It's basically keeping T log T. We knew about that. You get linear Q. Yeah. So what prediction? We had certain predictions for short noise, and we're thinking about various other magnesium quantities.
So what is this M star transition? Is some effective mass which is coming through the transition, or?
No, this is M star of transport. So one very important property of the theory is that the quasi-particle M star and the transport M star are very different.
I see.
And this just means it's the Kramers-Kronig transform of tau transport.
Further questions, Tricia?
You SYK model. Why SYK model has conformal?
Yeah.
Why?
Why?
In the first part, yes.
Well, it's a baby version of the this time parameterization symmetry. So that's the global conformal. This is the global conformal symmetry in one. Yeah, that is of course the key thing that we need. But if you take f of sigma to be a map from a circle to a circle, that will give you the formal symmetry. That's actually, this is a symmetry of the action. Just like spatial reparameterization is a symmetry of Einstein's equation, but it's not the symmetry of the vacuum. The vacuum is Lorentz invariant. Minkowski space of gravity is Lorentz invariant. It's not time reparameterization. It's only Lorentz invariant. Similarly, here, if you take the vacuum state of the saddle point, that only has a global conformal symmetry, not a local conformal symmetry. But then you have to then understand how to do the back end loop.
Do you want to say spontaneous symmetry?
It's almost like It's like a spontaneous symmetry breaking of a ferromagnet in the presence of a very weak magnetic field. There is a magnetic field we have to worry about. We can't set it to zero. If you set it to zero, the problem is not well defined.
Other questions?
Coming back to the observation in the cuprates,
Yes.
could you calculate also the whole resistivity or the whole conductivity or the whole angle?
Yeah, well, we are working on that. Let me just say. I mean, there were these early claims about two scattering times. And yeah, we're not sure that's the best way to describe the data. That's there are better ways to do it, which are consistent with a much wider set of data. But yeah, so just hold on. In a few months, hopefully, we'll have a paper on that.
Because there was some sort of experimental claim that if you divide the resistivity as a function of temperature divided by the whole resistivity as a function of temperature, you get a perfect square.
Yeah, so that's what I'm referring to exactly. Yeah, but that was the Ong Anderson thing way back when in the 90s. First of all, that hasn't been confirmed in experiments. It only holds some small temperature windows. Yeah, okay.
But in any case, it's possible to calculate. So you will.
Well, we're working on it. Let me say that's the honest answer. We're confident it's going to be okay, but let me just say, okay, we're working on it. That magnetoresistance and Hall effect is the tricky part. The other thing we worked on quite a bit recently is short noise, and there's a beautiful experiment, not in the cuprates, but oops. But in a heavy fermion compound by Doug Nadelson on short noise. And we hope similar experiments will eventually happen in cuprates. Yeah, I don't know. My computer's acting up. Yeah, I mean, that's, this is a field that goes back 50 years, and it's very hard for theorists to make a prediction because everything's been measured. So really, we are behind the experiment. We're just trying to understand and put together more than one experiment. So if we can both put together 3 or 4 experiments, which is where we are making progress.
Any further questions?
Yeah, so maybe I missed this, but where exactly does the net charge of the black hole enter the SYK Hamiltonian? So what is the corresponding parameter?
Just the charge of the SYK model also. So that's this phi of tau that I didn't talk about. So yeah, I mean, this is there's this cube here. So there's a net charge, and that gives you there's another zero mode, which I didn't mention. I just simplified that. So when in this path integral, in addition to this emergent time parameter symmetry, there's also an emergent gauge symmetry.
So it is also possible to see from the SYK perspective that the same calculation would not run for uncharged black holes, for example, where the
no. The SYK is living this charge has 2 roles. Yeah. One is it does affect the prefactors a little bit for the SYK model. This 1 over n had to do with the charged black hole. Charge SYK, excuse me. There's also Majorana SYK. No, the charge, played another role, which is the only reason we had charge. Otherwise, I wouldn't need charge for the black hole side, because only because of charge can I go from 3 + 1 to 1 + 1. Without a charge, I cannot do that. And that is not the physics of the SYK model at all. That's the physics of the Einstein's equation. And I can't say I have a deep understanding of it. So, but I have worked through the equations. And this connection, this connection here, yeah, from first line to the second line, it's a classic, it's a
gravity result.
Simple calculation, general relativity. Just doing general relativity, you go from 3 + 1 to 1 + 1. That dimensional reduction is a property of Einstein's equation, has nothing to do with the SYK. Once I get to this point, then I can celebrate because now I can connect it to the SYK.
Okay, there was another question first in the very back and then.
Extend this black hole formalism to the problem of whether or not the universe.
After what, sorry?
Whether the universe is expanding or not. Is it possible, or is it a completely different physics?
Certainly physics, I don't know. Let me say that. So there is a cosmological constant, and you can put that in this theory, and that will change some of these numbers. if you had a black hole and with a cosmological constant negative, well, certainly you don't want it to be positive, then it wouldn't be equilibrium, right? If you had a negative cosmological constant where the universe is stable, then all of this would go through. But where the cosmological constant comes from, I'm sorry, I have no idea.
Okay, now your question.
Yes, my question, we talked a lot about, you talked a lot about quantum entanglement. So
Yes.
my question is it possible that information could be transferred between planets in real time with entanglement? Because in terms of thermodynamic, it could be also a proof that white holes exist as well, because black holes.
Yeah, I'm not sure. I'll be out of my depth here, but I will comment on your word information transfer. So entanglement is not information transfer. Maybe that's the way to think about it. So, Einstein certainly said that spooky action at a distance, right? In fact, I even have he said it, and I even know the German for it. Let's see. That's always wrong. That was a more okay talk. Here we go. All right, so this is an actual quote from Einstein, from a letter that Einstein wrote to Max Born. Maybe you know this. Okay, you can read that. Spooky action at a distance. So that's, I think today the consensus is that's not the way to, that's not correct. So what's happening here, if you think about entanglement, is you have these, you have to create an entangled pair. So in the past, these objects were next to each other. And then you separated them. So now you run into contradiction if you somehow think that the quantum state sits here or sits there. The whole point is, the idea of a quantum state is not local. The quantum state is a global state. It's neither here nor there. So whether you measure this electron, that electron, you're perturbing the same state. So there's no information that went from here to there, because there's only information when, if Alice has one part of the equation and Bob has, and Bob does a measurement, then Bob has to call Alice and check whether their measurements are consistent with this particular entangled state. That's when information gets transferred, and that only goes at the speed of light.
But is it
Before
all?
Alice has spoken to Bob, nothing is happening in terms of information.
Yes.
My question is also about entanglement.
Yeah.
When you look at it experimentally, it's about correlation. When you look at it theoretically, it's about like you calculate things like the Neumann entropy. And my question now would be, when you look at the SYK model, how do you capture entanglement and how do you quantify entanglement? Yes, could you elaborate on that a bit?
Yeah, I think that's entanglement has many faces, like I mentioned. And entanglement entropy is one popular way of characterizing it. Hardly for black hole physics, that's very important because that's where the Hawking paradox is most stark, where you see a problem with the entanglement entropy as a black hole evaporates. That's presumably why black hole physicists are really interested in entanglement entropy of evaporating black holes. So those things have been computed. From a condensed matter point of view, that's not so useful because it's a thing that's almost impossible to measure. But yeah.
Yes, you said something that you had simulation of up to 25 particles.
Yes.
So have you computed something like the phenomenon entropy for that?
Me personally, no, but there are lots of papers where people have done such things. Okay. Yes, yeah.
Okay, maybe one last question. Use time.
A question also for the entanglement. If we consider subsystem, we separate the marijuana into two parts in the SYK model. And then are there any correspondence in the gravity which correspond to the entanglement entropy for the one part of the system?
There are these thermofield double states which represent wormholes.
But we consider single dot, single cluster of SYK. Are there some?
I don't know. You want to take an SYK about, cut it in half or something?
Something like this. Yeah.
Well, you would have to somehow split a black hole in half too, I suppose. I don't know.
Yeah, decimal. Yeah.
I mean, That doesn't stop, people in string theory talking about evaporating black holes. I mean, and what happens when you press the page time, and the page time is many orders of magnitude larger than the age of the universe, so not relevant for anything. So it's a thought experiment you can think about too, I suppose. I don't know. Yeah.
Okay, let's thank Sylvia again for the